All right, is it going? Today we're going to do things a little differently than usual, partially because the camera that I ended up borrowing from the library today, as opposed to other cameras, seems to cut videos off at about 25 minutes as a max. So I'm going to do 3 lectures today, a lecture A, B, and C, each of about 22 minutes or so. And the break between lecture A and lecture B will be very short, just a few seconds. And the break between lecture B and lecture C will be longer, about 3 minutes is what we're going for. In lecture A, I want to try to do that problem that we were working on Friday, except focus on the y-coordinate of the center of mass instead of just the x-coordinate. I was saying I wasn't sure how to find the y-coordinate. Well, I realized I could find it with something called the double integral. So I want to talk about that a little bit and essentially introduce you to multivariable calculus because of that. I am just going to try to find the mass of the Earth's atmosphere as well, amazingly enough, although we're only going to do it up to 100 meters high. Up to 100 meters high. Amazingly enough, if we assume we know a certain fact about the atmosphere, we can do that. Lecture B will talk about present values and future values of discrete payments. That means individual payments at certain moments in time, and introduce the idea of something called the geometric series, which is going to be very important for us in the next month or so. And in lecture C, we're going to talk about present and future values of continuous payments, also called income streams or cash flows. I want to also add in there as another name for it. Cash flows as another application. Okay, and this will lead us in Wednesday and Friday's class to talking about actuarial applications. We'll combine this present value and future value stuff with lifetime random variables probability as we finish off chapter 8. All right, so how do you do center of mass in general? For thin plates of metal, say, so we're going to keep it to be a 2-dimensional problem. We had a triangle last time, but let's just sort of draw an arbitrary blob as our thin plate of metal. So imagine you have a thin plate of metal shaped like a blob. Okay, not that you would ever create such a thing, but let's pretend somebody has. The density in general will not be constant, though it could be. And if it's non-constant, it's not necessarily constant along horizontal or vertical lines like we've been assuming so far. It could be something that varies over the entire thin sheet. By the way, there's another name for such a thin sheet. It's called a lamina. It's the other name for a thin sheet, a 2-dimensional sheet. You can imagine it to be a sheet of metal. Your density function, delta, could depend on both the x and y coordinates of your point in general. This is an area density, so this might be grams per square centimeter, for example. So because of this, because it could depend on 2 variables, that's why we call it multivariable calculus. Your functions can depend on more than 1 variable. You can't slice it just with vertical and horizontal slices. You have to slice it both horizontally and vertically. Got a bunch of vertical slices here, chopping it up this way, and a bunch of horizontal slices, chopping it up this way. Now, instead of the density being approximately constant along thin horizontal slices or thin vertical slices, it's approximately constant along the little tiny rectangles that my chopping this region up into results in. So you might have a little tiny rectangle like that. If it's small enough, the density is approximately constant, I could find the approximate mass of that little tiny chunk. You could write delta M for the approximate mass of the small chunk is approximately the density at some arbitrary point in that little piece times the area of the little piece, delta A, And the area of the little piece, I mean, if it really is a rectangle, I guess this is going to be an exactly equal to here, would be delta x times delta y. That would be the approximate mass of the little chunk. What about the approximate moment, say in the y direction, since that's what we want to ultimately find for that triangle? Remember we found this, the moment and the center of mass in the x direction last Friday? Say there's a y-axis in here somewhere, or excuse me, an x-axis. It could even go through the lamina like that. That could happen. It's always with respect to some coordinate system that you have a function like this anyway, right? You've got to have the coordinate system first before you can find a formula for such a thing. What's the moment in the y direction going to be? In other words, with respect to the x-axis, it's going to be the distance, the vertical distance between the x-axis and that little chunk, approximately, is y. Thinking of x comma y as being some randomly chosen sample point in that little rectangle. That distance is effectively y, it's approximately y. So the moment, capital M here, in the y direction with respect to the x-axis would be approximated by this expression times y. Y times delta of xy times delta x times delta y. Again, delta of xy is a function. Delta x and delta y are individual quantities. Delta x is the width of the triangle or the rectangle or the base, and delta y is the height. The total moment in that y direction then is going to be approximated by a sum of things like this. Letting delta x and delta y go to 0 then results in better and better approximations, and in the limit you get the exact answer as long as this function is sufficiently nice, like continuous, which I'm already assuming it is continuous. You get an integral. This is an approximation. The exact total moment with an exactly equal to is going to be an integral. But it's going to be a new kind of integral, a double integral instead of a single integral, because you have two quantities, a delta x and a delta y, that both go to 0. You got to integrate with respect to x and y. And you end up writing two integral signs typically. If this lamina has a name, call it D for domain, is sometimes the letter used. You sometimes emphasize the domain down there. The integrand, the function you integrate, is this product right there. You got a delta x and a delta y that are going to 0 in your summation. That's the function that gets integrated. Y times delta of xy. The delta x, delta y in differential form is sometimes written dA for a little area. But we can go ahead and write it as dx, dy here. You can write the two of them if you like. That is a conceptual equation for the total moment in the y direction. When we divide by the mass, we'll get y bar, the center of mass in the y direction. It doesn't tell you how to calculate it. As it stands right now, it's just an idea. And even though there's two integral signs, you still think of that as representing add. Add these things up to get the total moment. What about for our particular situation? For our particular triangle here, this is going to be the example then from last Friday. We've got a triangle like that. It's supposed to be an isosceles triangle, doesn't look like one. A little bit better looking. That's our lamina, our thin sheet of metal. And our delta function was actually just a function of x. It was 1 plus x cubed. Do you remember that? That was our function. Grams per square centimeter. Now that function doesn't depend on y. But these ideas still work. Even though the function doesn't explicitly depend on y, you could still think of it as depending on y. It depends on y in a constant way, you might say. I don't know if that's the best thing to say, but you might say it. Even though there's no explicit y in here, you could still think about it this way, and you could still do this the integral this way. And you have to do it that way if you're going to find that moment in the y direction, because for any fixed value of y, the density is not constant. It depends on x along the horizontal line. So you really have to do it with the double integral in this kind of situation. We did not have to do it with the double integral for the x-coordinate of the center of mass. How do you actually do the double integral? You do it as something called an iterated integral. Again, we're calculating the total moment here. The mass we saw was 1 gram. The mass of the lamina here was 1 gram. So whatever the moment ends up being, we divide it by 1 gram to get the center of mass in the y direction. Total moment in y direction with respect to the x-axis is sometimes the thing people focus on, because you consider this distance to the x-axis. Is going to be the double integral, but I'm going to write it as an iterated integral, which means I need an inner integral and an outer one. I'm going to use parentheses for emphasis. I'm going to have an inner integral and an outer integral. The outer integral, like on the board up there, is going to be with respect to y, and the inner integral is going to be with respect to x. Looking at the picture here, y goes from 0 to 1. And those numbers, 0 and 1, are going to be the limits of integration for my outer integral with respect to y. Now you might think, okay, if y goes from 0 to 1 by the picture, it looks like x goes from -1 to 1. But that would be wrong in this case. If you put a -1 and a 1 for the limits of integration for the x, you'd really be integrating over a rectangle if you did that. That would look like that. Without explaining why, in this kind of situation, for any fixed value of y, what you need to do is you need to think about what x varies between along this line as functions of y. These limits of integration are going to be functions of y because, well, this is not really an explanation, but it does make some sense. When you integrate the inner integral with respect to x, the x goes away. And you're just left with something that depends on y, which you're going to integrate with respect to y. So these limits can't depend on x, because I want the x's to go away. It's the intuitive reason why you want to think this way. The equation of this line was y equals 1 plus x. That line, that's a slope of +1 and a y-intercept of 1. And the equation of this line was y equals 1 minus x. Slope of -1, y-intercept of +1. The limits of integration for the inner integral I can solve for by solving these equations for x as a function of y in both cases. This one, subtracting 1 from both sides gives you x equals y minus 1. On this one, I'm going to do 2 steps at once. Add x to both sides and subtract y from both sides. I will get x equals 1 minus y. Those two things as functions of y are going to be my limits of integration. And when y is between 0 and 1, as it is here, y minus 1 is smaller than 1 minus y. So y minus 1 is going to be the bottom limit, and 1 minus y is going to be the top limit. And the function you integrate is y times delta of xy. Y times this. I'm going to go ahead and distribute the y through. I get y plus y times x cubed. How do you actually do this integral now? Zoom in if you need to. If it's too far away, how does it look? How do you actually do the integral now? Does it look okay? Mm-hmm. All right. The inner integral is with respect to x. So treat the y as a constant. Treat the y as a constant and integrate with respect to x. Just leave the outer integral as is. Note that y were a 10. Integrating 10 would give you 10x. Well, it's not a 10, it's a y, but pretend it's a constant. Integrated with respect to x, you get y times x. Y times x. Integrate this one with respect to x. If y were 10, you'd get 10 fourths x to the fourth. It's not a 10, it's a y. You get y over 4 times x to the fourth. This gets evaluated from x equals y minus 1 to x equals 1 minus y. In other words, replace x first with 1 minus y, and then subtract what you get when you replace x with y minus 1. And in the end, after you do that, you'll get something that only depends on y, which you'll integrate with respect to y. It's a bit of a mess, though we do get some cancellation, it turns out. Extra sets of parentheses here, I think. That's what you get when you replace x with 1 minus y. Now replace it with y minus 1. Yikes. Kind of a mess. It's not as bad as it looks. You actually don't have to expand these fourth powers. If you had to, you could use Pascal's triangle to help you do the expansion, if you know about that, binomial theorem. But they actually cancel here. Even though you've got a 1 minus y to the fourth and a switched around y minus 1 to the fourth, those actually do cancel because raising to the fourth power, it doesn't matter whether the opposite thing is in there or not. 1 minus y is negative y minus 1. It doesn't matter though because I'm raising to an even power. So they cancel because of the minus sign there. This thing and this thing don't cancel though because that's to an odd power, a first power, 1 minus y and a y minus 1, the subtraction. They don't cancel, in fact they add if you keep the ordering 1 minus y, for example. What I'm trying to say is the answer is going to be the integral from 0 to 1 of 2y times 1 minus y. That's what this simplifies to. Simplifies further to 2y minus 2y squared. We have to integrate that from 0 to 1. We get y squared minus 2/3 y cubed from 0 to 1, which gives you 1 minus 2/3, which is 1/3. So that's the moment in the y direction for this triangular example here. So the center of mass now, I got to divide that by mass, but we already know the mass is 1 gram. So in fact, the center of mass, y bar, in the y direction is also 1/3. 1/3 divided by 1 is 1/3. So y bar is 1/3 divided by the mass, which was 1, which is also 1/3. I think the x bar we found last Friday would be 1/15. So the center of mass, x is 1/15, I believe, or was it 1/10? Anybody have it in their notes, Andy? I think it was 1/15. And the y direction is 1/3. Did you find it?
Yeah, it says 1/15.
1/15, okay. So the center of mass is right there. So if you took this lamina, this triangle, and tried to balance it on a pin, you'd want to put the pin right under that point. Of course, nobody can put it perfectly under the point, and so it probably wouldn't balance. But theoretically, that's where it would balance, if you do it perfectly. All right? Do you need to know this? No, we will be doing more multivariable calculus later in the semester, so I thought it would be good to introduce it to you. If you take multivariable calculus as a class, maybe next spring or next fall, you'll be doing this kind of thing. So it's not bad to introduce it. And it does emphasize that sometimes you can't just slice things horizontally or vertically. Sometimes you have to do both.
Can you just explain again really quick the upper and lower limits in the integral that you did with respect to x?
Well, yeah, I don't really want to take the time to do that.
Okay.
I understand you want to know. But it would take us too far afield.
Okay.
I'm just trying to say that for any given y, the x value needs to go between these 2 points, but that changes as y changes.
Okay.
So you need limits that change in y. It's sort of an intuitive reason. Running low on time, if we want to finish by 22 or 23 minutes here, let me just briefly introduce what we're going to do at the beginning of lecture B now instead of the end of lecture A. Try to find the mass of the Earth's atmosphere up to 100 meters high. We're going to ignore complications like mountains and valleys. Okay? It's actually a problem in your book, and I think before we take a short break, we're just going to pretty much state what the book says here. The book says that the density of the atmosphere depends on the height above ground, above sea level, h, in the following way, at least as an approximation, 1.28 e to the negative 0.000124 h, and the units for this expression are kilograms per cubic meter. Now, what is this telling me? This is a function that's giving me the density of a height above sea level for the atmosphere. It does decrease as h increases. As you go up, this is an exponential decay. The atmosphere is getting less dense as you go higher and higher. So if you trust this, and I have no reason to doubt it, I'm assuming the authors got this from some source. It seems, strange enough that probably it's based on experiments and modeling and simplification and that kind of thing. It ignores mountains and valleys. Height above sea level here. We're going to be able to use this at the start of lecture B to try to estimate the mass of the first 100 meters of the atmosphere. We're actually going to be able to do that. But let's end lecture A right there. Is that there?